This little camera here is, what are you calling that? That's the B-roll?
That's B-roll.
Oh, okay.
Okay. Good afternoon, folks. We're here with Milton Heath of AddGlobe, the 4C podcast series. Today we're going to be talking about the High Flow Sampler. So Milton, tell me a little bit about the history, your history and your involvement with the High Flow Sampler, and then the history of the High Flow Sampler.
Well, thanks for being here and inviting me. So it's an interesting history. It started about 2002. I had just got into this side of the business when I was working at Heath, doing leak detection and quantification. It was a new thing for us because we were all about leak detection. So the idea of quantifying leaks was new and exciting. And so we had an opportunity to buy this business that Touche Howard had developed. It was called Indico Air Quality Services. Now this was a time frame when Enron collapsed. And so a lot of this work had been done to lay the foundation for all the emission factors that were out there, EPA, PRCI, Gas Research Council or Gas Research Institute.
Yeah.
So they were funding a lot of this initially. Well, it had a lot of momentum, and then it just petered out with Enron. And of course, it was kind of tied to the value of gas too. Gas was very high, so measuring emissions was a really important thing and fixing those leaks. And then it went down to nothing. So Touche got out of the business. He was looking for an exit, and we were there. And I was the driver to take over his business and learn and get mentored from him. So everything I knew initially, I was taught by him. And so he developed the first prototype high flow sampler. And he actually had the licensing rights to sell it. Well, Bacharach also had the licensing rights to sell it too. And there was some legal back and forth in there between the two companies, but Bacharach was already a bona fide manufacturing company. So they took this thing and ran with it. It was totally new for their company also. And so they rolled out the high flow sampler in 2002. Well, they were also looking for somebody to drive their business. And so this came together very nicely with us taking over Indico Air Quality Services, which eventually became Heath Environmental Services, Heath Professional Services, Heath Environmental Services. So I had the benefit of taking new technology, getting out there, doing the leak detection and doing the quantification, and selling their product and Heath products simultaneously. So it worked real well. And with that came the training programs too. You had to have something to be able, somebody to help do the training of the equipment too, and that was easy. So it was a bit of a rocky road at first, being new technology, and those first few years, because nobody was really throwing a lot of money at this after Enron collapsed.
It's exciting times, though, anytime you get to break new ground, develop the customer base, develop the training. That's a fun and exciting time.
It was, and so Heath had predominantly been in the gas distribution side of the business, and very, very limited in interstate transmission. So this was a big segue into that market. High pressures, lots of equipment, compression, and so this is where the big leaks occurred. Of course, on any given distribution system, they're managing maybe 10,000 leaks in a distribution system, plus or minus. Not so many in the transmission side and upstream, but they could be significant, right? So
much larger. Yeah. So the local distribution from 2 households to a pizza place with a gas-fired pizza oven, right? So that's the local distribution, and that was generally the stronghold for Heath.
Mm-hmm. Yes.
Yeah.
Indeed.
And then as the high flow sampler came to be, there was more of an interest in the upstream, midstream transmission to quantify the leaks on the production side, not necessarily the end user side of the equation.
Well, and so that's where a lot of the studies and the focus was on that market segment, interstate, not midstream so much, no, interstate transmission storage. And so you look at those early reports, I think there was a lot of effort in that particular area. And so the Bacharach unit was developed with distribution in mind and saleable natural gas, so clean, processed, and so the sensor technology too it worked well for that application.
Why was more of the focus on the sort of the transmission and end user? Do they think of it as a product at that point? So they think of it as loss of product? What?
Well, so my opinion based on experience, there was a lot of low-hanging fruit just for what they were doing in that market segment and the efforts that were made to do the inspections, the surveys, and they didn't have to look too far. Remember, there's no optical gas imaging during this time phase. Okay, that came in mid 2000s. So we're talking late 90s, early 2000s. So you couldn't see this stuff. But
yeah,
it's
interesting. It really changes the perspective because we were talking about this the other day. When you can't see emissions, you use regulatory compliance as a surrogate. So am I protecting the environment? Well, I'm complying with the regulations. Yeah. Then once you can see the emissions and measure the emissions, all of a sudden the perspective changes greatly. Mm-hmm. It's all about how much am I losing? How can I quantify that? It's just a different mentality. So before the advent of the OGI camera, which I think was in the 2002, 2004 timeframe, if you're talking about when David Furry
Yes.
invented the thing, up until the commercialization, even a commercialization may have been 2004, 2007, but at that point it would have been very expensive relative to the cost. It's still about 70 to 90,000 for one of those cameras, but that was 70 to 90,000 14 years ago, and it's still 70 to 90,000. So the camera, it hasn't been invented yet. We're using method 21, getting ppm measurements, which is a concentration,
Yep.
but no flow, no mass. All of a sudden, the high flow sampler comes along, and now we can quantify the flow and quantify the mass.
Yeah, so clearly there were other techniques being used. They were crude. They were challenging for setting the setup of it, and it wasn't instantaneous. So the bagging techniques, correlating equations. And so here you have this new device that works like a Method 21 instrument, taking real-time measurements, calculating it, and giving you an output. But it was very clear, though, back then, what Touche Howard was doing. He knew where to go. He looked into these places and discovered the three main areas where problems occurred that were overlooked. And again, sight unseen. And so those were your blowdown systems, all associated with valves, unit suction discharge valves, pressure relief valves, blowdown valves, and then your packing systems, rod packings, wet seals, dry seals off of turbines. And so, and the third category was the standardized components, just the pieces of pipe fitting together, swage lock fittings, threaded fittings, any connecting pipes. But it was the blowdown systems up high. You had to get to these places. So he did a lot of ladder operations back then, and hanging off of roofs with safety gear, fall protection ropes. He was expert safety guy and knew all of his knots too. And so he passed that on to me as well. And back then I could traverse all over these roofs. It was El Paso Corp. That was the big company.
Sure.
And you'll see photos of me. They would never allow anybody to do that today, but that was how we did it. So we getting up there, and so there was methods of being able to sample these stacks with a sniffer, just with a long telescoping probe, and pulling the sample into a combustible gas indicator, more or less, to just get that percent gas reading. And if it was there, then you had to make sure that was your next point of measurement. So a lot of that was ladders and off the rooftop. So
rope access was coming back to some degree at refineries, which I kind of find hard to believe that it. But I guess scaffolding has dangers and slip and falls. So. A little bit about the history of Andrei. So AddGlobe is distributing a new high flow sampler, and one of the key players with AddGlobe is Andrei. So a little history on Andrei, a little flavor on Andrei.
So I came to. It's funny. We're talking about Shell recently too. I was on a call with Shell here in Houston when this guy called me out of the blue. I forget how he got my number, but it was Andrei Gorski. And so at this time in 2005, we had just completed with Seth Baruch and Kevin James. These guys put together a methodology for the United Nations, AM0023. And I'm taking Touche Howard's methodology, leak detection, quantification, high flow sampler, and handing over all this documentation. And so they run this thing up the flagpole, and it becomes a new practice for leak detection out there. Nobody had done it, but when Russia signed the Kyoto Protocol, they ratified it, making it become international law. And so somehow shortly thereafter, I got a call from Andrei Gorski, and I'm in Shell. I think it was Chris Keiko back then. Paul Tupper was probably involved too. And I'm at their facility, and he's asking me about this high flow sampler. So these guys were interested in the technology because they wanted to use this AM0023 right out of the gate. So interestingly enough, the Russians hit the ground running with this methodology on a massive scale across not just Russia, but Ukraine, Uzbekistan, Moldova, Turkmenistan, all the stans out there. And so it was a matter of the mechanism being used, joint implementation and clean development mechanism. These were tools and projects used to go out there, find the leaks, quantify the leaks, and then come up with a fix. Reduce those leaks, and then they were looking to take the carbon credits, that was the end game. But they needed the means of doing this, so there was a lot of leak detection equipment. And so, where did half of the Bacharach High Flow Samplers end up? Eastern Europe, and Asia, Europe, and Africa, but the bulk of them over there, over 450. And so that was more than half Bacharach ever manufactured over a 15-year span.
That is really super interesting because we've done studies back at Sage. We did a lot of work in China and Italy and Spain and other parts of the world, and I've always viewed the U.S. as significantly ahead of everyone else in the world. Typically 10 to 20 to 30 years. You measure how measure how well a country is doing based off of how many decades behind the U.S. they are. That's kind of my measure.
Yeah.
We were recently in Brazil, and from flare's perspective, I viewed them as somewhere between the 90s and the 2000s, which isn't bad for most countries. Most countries, if they're 3 to 4 decades behind the U.S., they're kind of a laggard. If they're 2 to 3 decades behind us, that's sort of the standard.
Right.
And I don't really find very often, even, which was surprising to me when I went to the European countries. I assumed that the European countries were, somewhat on par with us or as clean as the U.S. If you read the newspaper, you'd think the European countries are way ahead of the U.S. and the U.S. is the laggard. Yeah. And if you're in the business, generally, that's just not true at all. The U.S., most of the technology is developed out of the U.S., most of it's researched and implemented and really commercialized in the U.S., and then finds a home elsewhere slowly over the coming decades. But that's interesting that Russia really took this on very quickly.
Well, let me back up before that happened. Ukraine's in the news, right? Well, Ukraine was actually the first country to really take this technology and methodology and go with it. So, and all the credit, again, to Touche, because Touche was there, and it was Cherkasy Transgas. It's about, hour and a half, 2 hours south of Kiev. And it's an area that has been well protected. They're still okay over there. But these guys were taking the lead in that region of doing quantification. And I sold the first Bacharach High Flow Sampler to this group. That was my first international trip ever, well, outside of Canada, that I'd ever been within. And so, and Touche had been all over Russia too. These were EPA projects. These were joint projects. So, but backing up though, Ukraine did take the lead in this. And these guys were over here for our EPA gas star. They were hosted by EPA. They came over here on a couple trips. Of course, Russia was very well involved with EPA gas star as well. They hosted us.
So when did Gas Star start? I didn't remember Gas Star being that far back, but I guess it was.
Interesting. I believe the late 90s. I got on the scene 2002, really. And so it was, who's the guy's name? Kevin, not Kevin. His name will come back to me. But he really did a lot of sowing of seeds internationally to get a lot of countries to participate. And he did a tremendous job. What's his name? Gee whiz, sorry.
That's all right. So the high flow sampler comes onto the scene. All of a sudden, we're going from ppm readings to being able to do actual concentration flow.
Volumetric measurement, right?
Volumetric. So the original high flow sampler is volumetric, but not mass. Not mass flow rate.
So it all, you have a combustible gas indicator using traditional, this conventional sensor technology, catalytic oxidation, thermal conductivity. That's what they used in the Bacharach sampler. And it had a 3M blower in there too, that to pull the sample. And it was about 8 cubic feet per minute, maybe a little bit more than that. And so you're just measuring the gas concentration and the flow rate. And
so you have a known flow rate and a gas concentration, so you do get the mass flow rate too. Yeah. Right. And was the original high flow sampler methane only or VOC? Was it a total VOC?
Well, no, it was total hydrocarbons. Those combustible gas indicators, you could put any hydrocarbon up to them, and you could get a reading. Now they're all calibrated to methane, right? So,
yeah. What's the relative accuracy? And I realize that it may be dependent upon the flow range. The lower flow rates and higher flow rates may not have the same accuracy, but generally, what was the accuracy?
10 to 15%. I believe that was That was what the stated accuracy was. So it wasn't the best. And you have a sensor technology that was difficult because there was this crossover at 5% gas by volume, and if you were measuring a gas leak in that range, it would get stuck, and it would be erratic. So you'd have to work hard to get your reading, and you have to look at it several times. But you had that weak area with that sensor technology before it'd cross over to thermal conductivity.
Less than 5%, it works well. Mm-hmm. Above 5%, it works well.
Yes.
But in this 5% range, it's not so happy.
Very frustrating, yeah. And it was sluggish and slow. I think a lot of the mechanics of the design features in the combustion chamber were not the best. Getting the sample in and getting it out, so it had a very slow response time. I was not pleased with it. So it was rife with issues, but let's consider it was first generation technology.
Yes, for its time, it was still revolutionary.
Yeah, and so it was the best thing you could get to get very quick real-time leak measurements.
Excellent. So how does that compare to the new high flow sampler? What are the features of the new high flow sampler? What are the underlying mechanisms?
So it was a long time in coming. They had a good 15-year run, let's say, with the Bacharach unit. There were very small tweaks to the software, nothing significant, button switch on the on-off. But the laundry list of items was significant, what people wanted. And the first thing was the most obvious, was the bulk of it. You open that thing up, the old one, it was just, wow, there's not a whole lot in there. So it was big, bulky, and it just weighed a lot. So on the new technology, it's less than half. It's less than 10 pounds. So it's very compact and easy to carry around a station now. The other one is just you're really hamstrung with, you got other tools you got to take on this too if you're doing this type of work.
Yeah, sure. The new one seems very, very manageable in terms of being able to use as an instrument.
Yeah, and so that one, checking that box was huge. That was the loudest thing that we were hearing from customers. Any measurement operator, that was pretty much top on the list. So aside from that, accuracy does matter, and so let's get a more accurate sensor. And how do you do that? Well, interesting, EPA did say we want a methane-centric sensor on this technology. That's what we're interested in. That's what all the regulations are being geared around. So AddGlobe went with a non-dispersive infrared sensor. It's an optic sensor, optic technology. So it'll see the full scale of gas without this crossover thing.
So a non-dispersive infrared sensor, how does that differ from, say, an optical gas imaging camera, a FLIR camera's image?
So the optical gas imaging cameras, it's a filter system. They're looking at a certain wavelength of the infrared spectrum. And so on this technology, non-dispersive infrared, well, you got gas coming through. There's an LED light in this sensor, and it's looking for a spectrum of gas. In this case, that is specific to methane. And so you have far higher accuracy, and tests have proven that you can get as good of accuracy as 1% on this technology. And so that's not realistic for field, though. Field 5%, because you're gonna have some challenges out there. You got to make sure you get 100% complete capture of every leak when you're doing that. But it's easy to replicate in a lab. You can get 1%. With this type of technology. It's been out there for actually a decade and a half, maybe. And so it doesn't you can't poison these sensors like you would the old technology. When you expose the old sensor technology to heavy hydrocarbons, impure gas, you're wearing that thing out. It's degrading over time, and there's actually a filament in there that's getting really, really hot, which consumes a lot of energy. So another reason why AddGlobe went with this non-dispersive infrared is it's super low power, and so low power is a good thing, coupled with accuracy, and that allows us to have a 10-hour battery life on one charge and over 65 hours of standby time. I mean, that's practically a full week of sampling, given the norm today.
Yeah.
So you might not have to charge that unit for a whole week, but you're not carrying around these big bad batteries like the Bacharachs.
Sure. It's no different than your phone. If your phone's battery runs dead, all of a sudden you don't have a phone anymore, and it's extremely frustrating. To be able to get through a workday or several workdays without recharging the battery is a big deal in the field for a technician.
Well, knowing where that battery is too is important. That Bacharach sampler, it was problematic. You had two big batteries you'd carry around that would give you about 4.5 hours, good batteries. And so anytime you looked at the battery display, there was nothing linear about it as far as the percentage, like where am I at with this thing? Do I have an hour left, 2 hours left? It only gave you a voltage. It didn't give you a percent. So you get a percent reading on this thing, and it is very linear. So if it says, if it says 90% on it, you've got 90%. That means you got about 9 hours left on this thing. So it's very helpful to have that information to know if I get down to that 30% level, okay, I should probably charge it that night.
Yeah.
So you didn't have, it was blind with the old system. So you have that assurance when you're an operator working a full day. Do I really need to charge this thing overnight?
Sure. If you got a team of a couple people at $65 an hour and you waste a half a day, it gets expensive in a hurry, right? So yeah, that's interesting. So the battery, you've got a better battery, and you know when the battery is going to die or not die, and you can keep it charged. The sensitivity, it's using non-dispersive infrared, so you, in the optimal conditions, you got 1%. Generally, you got 5%, in which, and we did air permitting for a lot of years. Mm-hmm. Anytime you have a number that's within 5%, to me, that's an extremely good number, because
good.
You rarely are going to know the time within 5%.
Yes.
I know there's a big discussion within Subpart F about when you find a leak, and now you go to calculate the emissions. Mm-hmm. What was the start time for the leak? Well, we would rarely ever know the start time of the leak within 5%. If it hasn't been sampled for 90 days, you may have to assume it was 90 days, whereas it actually may have just started yesterday. Mm-hmm. So yeah, a 5% accuracy in our business is an extremely robust number. So for all practical purposes, you're taking the mystery out of the equation on the mass emission rate side. You still have the great difficulty of knowing when it started. So that's fantastic that you get that level of accuracy. In terms of recalibration and how do you recalibrate, or does it require recalibration?
Yeah, so another thing about the sensor technology is the reliability and the drift factor. Looking at the old, you got a lot of drift on that low end, and we want to know what these low end leaks are. We're more concerned. We're going to do a lot more measurements on that low end in this day and age. Drift is a factor, and with NDIR technology, you have a stability and a reliability unlike the old sensor technology. So you don't have to calibrate this stuff as frequently. We recommend calibrating once a month. And it's up to the operator how often they want to do a daily test, a verification. So taking a known amount of gas, just putting it in there, and seeing where it is. And you can just document it very quickly by the press of a button to save your recordings.
So is there a direct hookup to CalGas, a bottle of calibration gas?
Yes. You can take the old calibration bottles, the old type of calibration kit, and use it the same fashion. These little channel pumps that are in there pulling about 1 liter per minute, so there's really no change on the flow rate. So you introduce that gas at a low level. We're specifying 2.5%, same as the old standard. On the new standard, EPA also wanted a mid-range for the calibration gas, as opposed to a super high range, 99%. And so we're specifying something around 50%. You could use anywhere from 40 to 60%. It doesn't matter. But you dial whatever you've got, that certified gas, you just dial that number in on the screen, set it, and then introduce the gas. And once it stabilizes, you press a button to adjust the gains on it, and you're set. And you've got that locked in as timestamp when you've completed that task. So.
And that stays with the machine, with the calibration record is part of the machine's log?
Yes, it is. You can offload that as you can the other data files that you've saved with it. So it's useful. You couldn't do that very easily with the old technology again, but the regulators, I've heard there is instance out there where they want to see the records. So if you get caught and you don't have it, it's going to be on. As long as you haven't deleted the files off the device,
it's on the machine.
You can go to a computer and offload these files to show them by time.
Yeah, that's very, very useful. Which components of the oil and gas industry do you believe are going to find the most value and use in the high flow sampler?
Which components?
Say upstream near the wellhead, at a tank battery, a gas processing plant, transmission. Do all of them need this high flow sampler?
So it's a good question. Let me back up. So how many leaks could the Bacharach sampler quantify on any given natural gas facility? Compressor station is what I have in mind. There's thousands of components there. And so over years of work, it became apparent that tool could measure 99% of the fugitive methane emissions that you would find at a given facility. So that's pretty good. What are you doing with those other 1 or 2%? How they far exceed the limit of a high flow. So you got to come at it a different way, and that was where you do it with a calibrated bag.
So they were too high of concentration for high flow sampling?
Flow, so too
high flow.
Yeah, we're talking volumetric leaks, typically associated with packings, valves again, dump valves, storage tank emissions. So this was the other thing people wanted. They wanted a higher flow rate. They wanted higher capacity than they were getting from the Bacharach. So we really did check that box. We added 50% more capability of the sampling capacity on the gas flow meter. So we're going from 8 cubic feet effectively to over 12. In this case, it's 12.36 cubic feet per minute. So we can measure even more emissions on that rate. And so there are often times out there you will find one super emitter on site associated with the valves that you're going to have to fill it with a bag or some other source. They'll far exceed 50 cubic feet per minute. So you can
at that point, that would be a safety hazard, though. Right?
It would be, and so it'd be very difficult to do that, to get to that and do it safely. And it is possible to do that today with an optical gas imaging camera. Accuracy's, you can get 20% accuracy with a camera, but and you might attempt to do that with an OGI. But if you can't do it with a high flow, those super emitters, that 1 or 2% that you might have to do with an alternative approach.
Yeah.
And you got to fix those leaks anyway, right? You can see them clear as day with the camera. They're a problem, right?
Yeah, and the largest leaks account for the bulk of the emissions historically. There will obviously become a point where that may or may not continue to be the case, because once we put in continuous monitoring and we find the leaks the day of, the super emitters won't. Right now, the super emitters, if a super emitter goes for a month or 2 months, that mass can overwhelm any small leak. However, once you go to continuous monitoring and you find each of those super emitters on day one, now the very small leaks that persist for months or years could become more meaningful as a percentage of the total emissions, which really will just make your equipment even more valuable. Correct? Once the satellites are finding those super emitters on a very, very short time frame, and there's continuous monitoring at the facility, say a sensor or 5 sensors. So the 5 sensors pick up a leak. They know there's a source location. They may even help identify a potential source location as a box. But at that point, you then have to use some other device to locate the exact source.
Yep.
And how does the quantification, the accuracy of the quantification of a high flow sampler, how does that compare to the quantification of a OGI camera?
It's actually very significant. It's direct measurement, so you're going up to the source and you're getting all the accuracy you need. Again, in this case, you can do better than 5% with the gas flow meter. And it's repeatable if you're going to the source in a wide variety of conditions, because you're taking that leak and sucking it into the instrument. You're connected to it. OGI has its limitations, and it changes every single day, and it changes by person. So if you're trying to observe that leak, and hopefully you have a good enough plume characteristics to be able to quantify that leak with an OGI camera, because you really should. It's helpful in the imaging to be able to see the plume and characterize that plume, lining it up in a sweet spot with the crosshairs.
Yeah, I know what you're saying. If you took a OGI camera and you looked at a leak from one angle, then you moved over and looked at the same leak from a different angle, you may get a different answer based off of the background. Yeah. Whereas with your device, you're pulling the leak in, so you should get the same. Well, you don't really have a different angle, right? You're just capturing the leak.
As long as you're getting complete leak capture, it doesn't matter who's doing the measurement, right? And it doesn't matter what time of day it is, and really the temperature. Those are all variables that will highly influence OGI measurement. and temperature, right? Temperature is super important, but I will not discount the value of this OGI capability. It's come a long ways, and so granted, the last decade we've seen this huge paradigm shift with EPA Subpart W. It's no doubt forced operators to fix all this low-hanging fruit that's out there. It's uneventful for me to go out there and survey these facilities today compared to back in the early 2000s, where it was like, what are we going to see today? 1, 2, 3, or 4 super emitters at this facility.
Yeah.
And so we're spending a lot of time chasing those leaks down, just trying to wrap our equipment around it. But OGI, though, on those 1 or 2 super emitters that are out there, they'll probably have good plume characteristics to get a semblance of a fairly accurate quantification with the cameras. How good is it going to be?
Depends upon the conditions.
Right, 20%, and we've heard it could be as good as 10% under ideal conditions.
Yeah,
it's
so
still out
it's
there.
not a cloudy day. There's no wind. You got a good temperature differential. Yeah, we're working with the hyperspectral imaging, and there's a temperature differential is still required, and then the distance is also a factor. It can either be in your favor, work for you, or work against you.
That's right.
But in your situation, you have a much more reproducibility of your answer. The answer really shouldn't change from one day to the next.
Right. It can fluctuate a little bit on certain packing measurements. You can have an oscillating effect. And so now EPA said you got to be able to do continuous monitoring with this equipment if it's going to be compliant. What do they mean by that? Well, from the time you turn this gas flow meter on, it's recording data every 1 second, 1 to 3 seconds. So everything time stamp, all the measured and calculated values. Until the time you shut it off, it'll retain 50 hours of data on it. And so if you want to look at a leak for minutes, it doesn't matter how many minutes you want to look at it, you can average that data out if there's any swings on this stuff. And getting back to cameras, though, you want to look at a leak plume for at least a minute to size up the average, the max, the min, the average, to allow the calculation software to do what it needs to do. And I do think Ram Hashmoney is on top of his game globally in this arena. He's a mathematical genius. He's brought a lot to the table to bring the accuracy to the forefront with all the variables. So they're making it simpler for operators to do this. And realistically, operators, they're not going to have to do a whole lot of measurement, in my opinion, with cameras. It's those super emitters that it's going to be a safe application to use. And you wouldn't want to do those with a high flow anyway, because it could be dangerous and it's probably going to be out of the range, right?
Yeah. The concept of a single technology providing all of your answers and providing all the solution, I am very happy to see that go to the wayside, which more and more it is. Method 21 has a place. The high flow samplers have a place. Optical gas imaging has a place. The continuous monitoring, the sensors like the Cube and the Molex, they have a place. The satellites have a place. It's the layering of technology that allows for the greatest emission reduction, because each asset class lends itself to a different type of technology. And it's interesting to look back. the optical gas imaging camera, when it first came out, and I very first saw David Furry speak, I think it was at a TCEQ trade fair.
Okay.
I thought, oh my gosh, this thing's going to take off. It's going to completely revolutionize the industry. And then the AWP came out, and it required annual monitoring using Method 21.
Mm-hmm.
And so most folks didn't do it. But the optical gas imaging cameras were still so useful from a safety perspective.
Yes.
And from turnarounds, startups, and shutdowns. They gained wide adoption sort of despite the regulatory hurdles that were thrown up before them. Mm-hmm. And now it's interesting to see these new technologies. All of these new technologies find a home because they have operational benefits. The more tangible things become, especially from an operator's perspective, if the operators get this high flow sampler in their hands, and so they can see the flow, they can see the emissions, it changes their behavior because now this is a loss of containment. Mm-hmm. It's one of the things that I've always taken a lot of pride in our industry is the LDAR technicians in our business. They have a tremendous amount of pride in doing a great job of learning the regulations, of finding leaks, using the proper dwell times. If you talk to someone, from EMSI, which is now Alliance Technical Services, or from Think, they have a lot of pride that their technicians do a great job and that they have a great program, and it's so fulfilling to see where we've come to in the industry, where these people take so much pride in their workmanship.
Right.
With the acoustic sensors, Distran out of Switzerland has an acoustic sensor. So the acoustic sensor can see leaks of hydrogen and oxygen and nitrogen because it's working off of the sound. Whenever a fluid goes through a small surface, it gives off an acoustic signal. What most of us recognize an acoustic signal is a whistle, right? That's a whistle, makes sound. Right. So these Distran's acoustic sensors, when you put those in the hands of the operators, all of a sudden they want to go find all of these leaks because they take pride in being an operator in a unit, and they want that unit to be an extremely well-run unit. So they want to find any of the leaks because all of that's waste, of course. Even compressed air, losing compressed air is
absolutely.
You still have to have a compressor over there, or whether it's supposed to be under vacuum and it's losing containment and letting air in where there shouldn't be, or if it's even nitrogen for blanketing and you're losing nitrogen. All of that's a loss, and those operators, they take pride in running a unit well.
Right.
And so it's interesting with this high flow sampler with AddGlobe, as the producers purchase these high flow samplers, and the folks in charge of the assets, the operators out there in the field, if they have access to these high flow samplers where they can see that leak, quantify that leak, how does that impact their behavior? It'd be interesting because I'd guess that they would take a pride in eliminating that loss of containment, eliminating that leak.
And you mentioned UE. That's a coming technology. I agree. There's going to be some application broader with that. It's an evolving technology, and these operators who do the quantification though with high volume sampling. Your traditional LDAR surveyor, they think of a leak in terms of ppm. That's their language, right? And so, and EPA has its leak definitions, 500, 10,000. And so once you introduce the ability for that operator to now quantify that leak, they really know information, and they'll get good at being able to know leak characteristics even before they're sampling and quantifying them with the sampler, just by the bubbling effect of it on these small leaks. You can only do that if you're quantifying with an accurate device. So these technicians are becoming smarter and more valuable along the way, and that's good for industry, right?
Yeah. Oh, yeah. Concentration is one thing, but having a mass emission rate is more tangible to the operator. They know what they're losing in terms of methane, pounds of methane per hour, grams per second, as the EPA uses of grams per minute. Well,
and that seems that threshold, that definition of a leak, what is it doing? Isn't it continuing to just go down as far as
Sure.
what they define as a leak? It's yeah.
What we find acceptable as a leak point that we become better at if a valve, let's say to manufacture a valve, you've got to use the metal, so you've got the emissions associated with producing that metal. You've got to then cast the valve, you got to machine the valve, you got to paint the valve, you got to transport that valve, you got to store it in a warehouse for a while. Mm-hmm. Now you have to transport it to the site, you have to decommission the equipment and install it. And so the CO2 equivalence of a valve is a number that we're not yet there as an industry to say, okay, we're better off having that valve leak at 250 parts per million even for 10 years than to replace that valve, because the CO2 equivalence of that valve is higher than the CO2 equivalence of the leak itself. Mm-hmm. We're not there yet. I believe we will get there as an industry, determining the CO2 equivalence of a life cycle of a valve, or life cycle of a piece of equipment. Obviously, if it's a very small valve, it would have a much smaller CO2 equivalence to replace the valve. But a very large valve would never make sense to replace that for a 250 ppm leak, 250 ppm concentration leak. Mm-hmm. And of course, the beauty is we won't be thinking of it as 250 ppm concentration. Right. We'll be thinking of it as a mass flow, because we can measure the mass flow as from an AddGlobe High Flow Sampler.
So this recent EPA proposal, a couple announcements came out, one this week on an update, and I'm still wrapping my brain around it. But it looks like they're really after stronger data. They want empirical data. And so subpart W, there was a lot of emission factors being used, right? Thrown around.
Correct.
Certain companies, I heard, were doing their own measurement to get company-specific emission factors, which is very good for those companies when they're way under the standard emission factors that are being reported. So they know they have a knowledge base. And how can they get that? Well, you can only get that.
All of those are the questions that are out there.
Yes.
Good or bad or otherwise. Those are all the questions that are out there.
Yeah.
I think there's also some question around if a date will be set in the future when do you want to quantify with empirical data? Mm-hmm. Those are all questions that people should talk to their attorney about. And the use of the high flow sampler. When is the best time to use that a high flow sampler? What percentages do? Are there any universities currently engaged in those studies?
Well, the one that comes to mind, the predominant one here in the United States, Colorado State University, their METEC facility, that's the Methane Emissions Technology Evaluation Center, Fort Collins. I don't want to take any credit away from UT, right? Here we are in Texas. David Allen's doing some great work, right? He's been all over this stuff too. It just so happens though, Colorado State though, they're more of an equipment evaluator and have been. They got a facility there. I'm familiar with it. I've been in and out of there, and of course they host the the CH4 Connections
Yes.
Conference annually with the Gas Technology Institute. So CSU, UT, who else out there is there?
We'd love to see Texas A&M on that mix. Being from Texas.
Well, you'd think that they might, get into this at some point with the agricultural focus.
Yeah.
A lot of cows out there, right?
That's an interesting question. Do you have some applications on the agricultural side?
I do not. Yeah, we're natural gas focused. That's our lane, right?
Yeah. We'll have to get into that because there's a great graph out there that shows the methane sources in the United States, and this was a 2020 graph, and it shows natural gas production, natural gas industry was 26% of the methane emissions. Agriculture was 25% of the methane emissions. Well, we know based off of the refining industry, so if you look at the refining industry, they achieved a 90 to 95% emission reduction on the majority of the pollutants. If you get them, I think from 90 to 2000, they did about a 75% on average reduction. But if you look at over that 20, 30-year period, they're easily in that 90, 95% reduction. Methane from the agricultural side will very quickly become the largest source of emissions because we know the oil and gas industry is going to hit a 75 to 90% reduction of methane.
Right.
Within certainly within a decade. And they're very far into that decade already.
Well, the walls are closing in. The wagons are circling, and got all these technologies, as you mentioned earlier, that are coming of age. So the knowledge base. So you think of when EPA saw Dave Furry's invention with the camera and the wow factor.
Yeah,
it was so powerful that it had staying power. They knew they were going to unpack that thing, and it wasn't going anywhere. And the result has been, the remarkable amount of just the safety side of it. Forget about emissions just for a minute. The safety side of it, what can you put a price on that? I mean, avoiding catastrophic failure, human life, loss of facilities. I truly believe OGI has served and checked that box off first and foremost. Emissions, secondly to that, the knowledge of emissions. And so, but now as we enter the age of being able to look at equipment 24/7, there's going to be this new layer. We're in this new paradigm shift where, okay, we're in there. We know this thing, what this thing does. We look at it annually. and we come back to it, we survey it. Now it's, wow, we're going to look at this stuff all the time now, and we're going to get this empirical knowledge base. So the equipment out there, we can fix equipment. Industry can make these leaks go away. And it's really, in the big scheme of things, it's directed inspection and maintenance on a massive scale when you can see what's going on from 30,000 feet. Because up until recently, we've only been able to look at it from here to there, right? And one time, we're here and gone. But what we're talking about is definitely going to move the industry's emissions, far, they're going to get way down on a scale, and they're manageable, they're controllable. When you talk agriculture and you're talking emissions from cows, okay, this is something we live off of. What are you going to do to make that thing go away? Are you going to remove the cows?
No, it's much more difficult.
I don't see those numbers changing, but I think I agree with you that the natural gas industry is only going to move in this good direction as a result of all of this.
Yeah, there was a great article today saying that the emissions in the Permian Basin are likely to decrease by 75% over the same time frame that the production increases by 40%. If I were a betting man, I'd say that's already happened over the last decade.
Yeah, I would agree with that.
With what I know, the industry has done to eliminate the low-hanging fruit, the larger sources. Yes. We've already gotten a lot of the larger sources, and now we're going for smaller sources. But it turns out there is a phenomena that even though your sources today, because I know you talked about when the High Flow Sampler first came out, you would go to any site and see 2, 3, multiple super emitters.
Yes.
Nearly every single site you went to.
Yeah, about every other facility you could expect 3, 4, 5. You were likely going to get 1 or 2 back in the day. Now you're lucky to get 1, right?
Yeah, oh yeah, for sure.
Yeah, it's not as interesting.
We talked to HSE director last weekend as part of the 4Cs planning team, and he mentioned the number of leaks that they have. And, of course, over the last couple of years, it's gone down to a fraction of what they used to see. And part of that is an awareness. But every time a new technology comes along, even though we took the emissions from 100 to 10 and we got a 90% reduction, so we think it's going to be even harder to go from 10 to 1. Mm-hmm. But it typically isn't, because the new technology works in a different way. Mm-hmm. And you end up achieving these quantum leaps, one after another after another. And that's why I believe we'll get to the point where we're looking at the CO2 equivalence of the piece of equipment that we're replacing, where to replace a valve, it takes energy.
Oh my gosh!
Yeah, lots of energy. So
just the cost of the steel alone,
sure,
and the whole value chain.
It has a huge CO2 equivalency, and so we'll get to a point where we know the CO2 equivalency of a piece of equipment, and then you would know the leak rate that would correlate to the remaining life of that piece of equipment. Mm-hmm. And that'd be a really cool day when we get to that point. You talked about the continuous monitoring, and it does bring up a topic that is the spatial and temporal factoring versus periodicity. And once we get where we have continuous monitoring and we know there's a leak because the sensor's telling us there's a leak on that particular asset, whether it's a tank battery or a wellhead or a one unit of a gas processing plant, or a 10 by 10 box of a gas processing plant. Mm-hmm. And then you go out with the high flow sampler, and you can determine the quantity of that leak. That's really a game changer. It's really a game changer because we're not going out once a quarter or once a year mm-hmm. and finding 10 leaks and fixing those 10 leaks. Every time a leak occurs, we are alerted, we quantify that leak right. and fix the leak.
Yes.
And all of a sudden this idea of, verification and of a certified gas.
Oh, yeah.
We could have a methane intensity number that would be more meaningful. Today,
beyond a shadow of a doubt.
Yeah, today that we can calculate the methane intensity. We know how much gas we produce, and we can estimate our methane emissions. But the problem is when we find a leak, we don't know when that leak started. So even with your amazing 95% accuracy,
yeah.
if the leak may have been going for 1 hour, it may have been going for 24 hours, the quantity of methane lost is still, for the most part, a mystery. It's a
yeah.
very scientific, wild-ass guess.
Isn't that what they're after, though? They're closing the gap on that. And look at how many players are in the industry looking to they want to be first to market on that. You got several companies out there that are pushing the envelope. But that advance in technology, from the moment it's detected, sending the person in there, they know they have a beginning time of the leak, and yes, sending somebody in there to do that direct quantification is something they need to do during this period of time because there seem to be huge differences between what the continuous monitoring, which is not direct, it's an indirect approach to trying to quantify that leak, and what they're saying, or what that calculation is saying, and what a direct measurement is saying. I think they're trying to get those correlated and lined up to understand. And
sure.
The game is on. The game is on for these technology providers to be able to, figure that out, right? Without having somebody there on the ground. But right now, it really is going to require, they get a trigger, they get an alarm. They don't know where it is, generally speaking.
Correct. They know there's a leak at this tank battery or
yes.
at this wellhead or at
maybe
this
some cases
unit.
They know, right? There are instances where they do know it's coming from this battery. They're closing the gap on that, right?
Oh, sure. The Emerson technology is a very interesting technology on PVRVs on tanks. Mm-hmm. So when you start pumping a liquid into a tank, the tank fills, the volume at the top of the tank starts to get smaller and smaller. The pressure builds, obviously, ideal gas law, PV equals nRT. So the volume gets smaller, the pressure increases, and eventually it's enough to lift the mechanical vent valve, a pallet valve. Mm-hmm. If that pallet valve, once the pump is kicked off, if the pallet valve doesn't go down and reseat, mm-hmm. then it can send an alarm. And so in that case, they would know immediately that this valve, which was supposed to reseat, is not reseated. That's a contact type switch. Yeah. They probably use magnetics now because they obviously wouldn't want that to have a spark. So it's a magnetic reading. But in any event, yes, in those cases, they would know that it's from this tank.
Right.
Now, and that would be a great application for a high flow sampler.
Yeah.
Because here's a tank, the PVRV is open. How much is that tank emitting to quantify that? That would be a fantastic application of a AddGlobe High Flow Sampler. Put that on that tank vent and it would tell you exactly how much it's spending. And it's probably the only way you could really do that, because the methane concentration inside that material would determine the leak rate, so it would be different every time. Mm-hmm. So it'd be a fantastic use of your product.
So, backing up, did I answer all those questions right? We got on a discussion about Andrei.
Yes.
And did I unpack all of that well enough? Ask me any other questions.
Well, it's just interesting to see how when did that occur, and how well did they use that data? How much data did they get? Because when we look at our data, most of our data was from bagging studies, either done in the 70s or 80s. We redid a bunch of those in the 90s.
There you go, the bagging studies, yeah.
Yes.
Part of that effort, weren't you?
Yeah, I remember those. I was a kid right out of school, and we built those bags. I remember having duct tape and putting a bunch of the stuff together and duct taping around a valve and hooking a volumetric flow sample to it, and then you would take a sample of inside the bag and go to the lab.
Yep.
And well, I remember one particular time we had gone to Las Vegas, and we were up quite late, and I was taking a math class at University of Houston at the time, and my math class, I had to take the final math test at like 7 o'clock that night, and I'd gotten back from Las Vegas at like 7 in the morning and went straight to the plant, and we're building the bags and putting the duct tape out there, and all of a sudden the alarm goes off, the shelter-in-place alarm, and we all go into the lab, because the lab had a contained air. And so we go into the lab, and we're sheltered in place, and I'm watching, back when you actually had a watch, because I had to get out of there at 6 o'clock to get to downtown to the Houston campus to take my math class, or my math test. And I'm just dog tired, and we'd been going back and forth from the lab out there building those bags and duct tape, and you're sweating, and it's just awful. It's Houston, it's in the summer, and now all of a sudden you get stuck in this shelter in place, and you're worried you're going to miss the math test. And I just got crazy lucky. About 5:30, 5:45, they ended the shelter in place, and I got to take off and went and took the math test. But yeah, I remember those bagging studies, and when people use those correlation equations and the emission factors, and sometimes they say, well, how are you going to quantify the emissions if you don't have the data for the emission factors and the correlation coefficients? And I can't help but think, like, those correlation coefficients and those emission factors, they are very wild guesses based off of studies that were absolutely less than the most robust scientific studies ever conducted.
It sounds brutal.
To me, it's a wonder that they still use any of that data.
I admit, that was not my thing. I came into it, I had it easy.
Yeah,
I never had to do that. But you're among a few elite people out there that I know.
I'm too old. That's what it is. I'm too old. That was 1990 when we first did the I did the bagging studies. That they were reworking some of the original bagging studies.
Right.
So Buzz Harris who's kind of the godfather of our industry, if you will.
Was Matt Harrison in that group?
Oh, yeah, Matt Harrison, Buzz Harris.
I know Touche Howard, he was doing a lot of that too before he developed the first high flow.
Yeah. Indigo was a famous name back then. So was Radian, the old
That's
Radian
right.
Corporation. Yeah. So all those guys are the
Jeff Panik's group?
I'm not sure if I worked
David.
with Buzz mostly. I was 21, 22 years old at the time. And Buzz was the goddess,
sure. Yeah.
the god of our group, of our business. And of course I had an opportunity to work with Buzz later in my career when he came to join Sage. And even today,
good hire.
Yes, the Lifetime Achievement Award at the 4C conference is the Buzz Harris Lifetime Achievement Award.
Pleasant guy to be around. Yeah.
Oh yeah, absolutely. Absolutely wonderful human being, first and foremost. And he did a fantastic job of mentoring. Buzz always had time for questions and answers, and it's kind of a lost art today, the old school mentoring. We had a lot of questions and answers. I remember I used to go into Buzz's office, and David ran him for a while. Buzz and David shared an office together, and both those guys, of course, were just amazing human beings, but also just a wealth of information.
Sure.
Anything that you wanted to know about LDAR or leaks or fugitive emissions, you could go in there and ask them, and they'd give you 4 different answers. Because that's the way it worked usually. EPA'd give you an answer, and industry'd give you an answer, and then there was kind of the official scientific answer, and then there was the reality, what you would do after you distilled all of those, the EPA approach and the industry approach, and then the underlying science. You put all that together, and you have to go take a course of action. So
you clearly were influenced from very few people when you add them up, and I too. I got my baseline of information. I was mentored by Touche firstly. He handed his business off to me. But the other guy who had a lot of influence on me was John Cordaway. He was EPA Gas Star Implementation Manager of the Year for El Paso Corporation. He taught me everything I know about rod packings. Now Touche, he knew about it too, and that was a central measurement that EPA that really opened things up for them, is to keep a tab on that early on, and then
still very much in the news
today. It's not going away, right?
Correct.
But that is one of the key measurements that the high flow sampler and the gas flow meter 2.0 critical. Those things can fluctuate, and so, but the intricacies of how those packings work, I don't think a lot of people still to this day understand how they work and why they do what they do. But they're much more in control today than they ever were. But they're always subject to go bad because there's a lot of moving parts there in constant motion, more than any other area of the compressor station, I would venture to say, as far as a potential leak source. Would you agree with that?
Yeah, well, anytime you have a compressor, you're dealing with moving parts and high pressure and degradation over time. And it's in the chemical industry, the refining industry, as well as the oil and gas transmission. It's always going to be a factor.
Yep.
And really, one of the things that comes in is a digital transformation. The readings and the number of readings that they take today allows a much more predictive analysis, and leads to eventually, we hope, that we as we gain more real-time knowledge. It's one of the huge factors in that this temporal and spatial scoring. The beauty of continuous monitoring is that we know when a leak occurred, so we're much better able to identify the cause of the leak.
Yes.
Once you identify the cause of the leak, now you can gather data to predict when the leak will occur and then to take mitigation measures before the leak occurs to prevent the leak from ever occurring because you're using predictive data. That's where all the digital transformation comes in. And it's super cool, too, the machine learning. I love the concept of machine learning. This and the number of technologies that can see emissions at lower and lower leak rates, because the earlier you see an emission source, the earlier you see the leak developing, the more data that you can gather about when a leak grows. And so, that's a whole other very interesting part of our science, of our world, is the question of, does a leak grow, or was the leak created out of chaos? In other words, was there an event that happened that caused that leak to very quickly become a large leak? Right. And on the refining petrochemical side of the world, they know that's in that 40 to 60% range. 40 to 60% of the leaks are because of a very slow degradation from a mechanical actuation or mechanical use, whereas 40 to 60% of them occur in a very short time frame because of an event. Right. So they have a cause, and they can be eliminated. As we get better data using the AddGlobe High Flow Sampler and other techniques, we know when a leak occurred, and we know the mass emission rate. All of a sudden, we know which leaks we want to spend the time to focus on to identify the cause and eliminate the cause. And in subpart W,
prioritization.
That root cause starts to become, and that, in the environmental world, the root cause is more of something new, certainly that being integrated into the regulations in the last 5 to 10 years. Whereas in the safety world, they've had root cause as part of the standard. In order to improve performance, you have to have a root cause element. The root cause element is what allows you to identify the cause and therefore eliminate that cause in the future. So if you think about it from the safety world, if you have someone gets injured because a grinding wheel breaks and then throws a piece into them, well, you put a shield on that and a guard. And so you don't want that same cause injuring someone a second and third time. Obviously, those guards get removed all the time, and then people get injured again. Then you have a much more complex problem, which is a human factors problem, which is how do you keep people from removing shields and removing safety devices, which is a much more common or much more difficult problem than simply designing a safe process. But on the emissions side of the world, we haven't really gone there. We're still in the discovery stage. We want to find the leak. We want to quantify the leak. But the concept of saying, I want to understand the underlying cause of all leaks and then eliminate that cause through predictive analysis, that is more still on the forefront. I say that we've obviously eliminated a tremendous number of emission sources as an industry over the years.
And they don't get the credit that's due to them for all that work that has been done, in my opinion.
Correct. And obviously we've reduced emissions by 90 to 95% across multiple industries. the oil and gas industry is certainly headed in that direction to a 95% emission reduction. It's still, but we have more room to go.
Yeah. Sure.
That's the exciting thing about our
boring.
business.
Yeah. Right. And now the prospect of taking this and expanding it out, because the natural gas value chain, it's massive, and so to see it go all the way up to production, getting outside of the area of transmission and storage, midstream, processing up to production, and it's expansive. Clearly, that's what's coming. More expansion and frequency of it, and I think it is necessary for a time being until they get an understanding of what it is, how these things tick, and they'll make a lot more of these. They'll bring the numbers down inevitably as a result of it, right?
Correct. And I remember the first time I did a calculation. I took the natural gas, not the first time I did a calculation, but of the value of fugitive emissions. I took the total natural gas production in the world, 5% lost and unaccounted for gas. That was the number. That was the starting point before we reduced methane. Started down this methane journey that we've been on for the last 20-some, 30 years. Took the total natural gas production, 5% lost and unaccounted for gas, the dollar per cubic foot, and then calculated that as an annuity. So what was the net present value of the all lost and unaccounted for gas at 5% lost and unaccounted for gas? And it was over $1 trillion.
Jeez. Yeah, that's a big number.
Yeah.
I knew it was going to be big.
Yeah. So that's when I knew, like, this is not going away. This will be a lifetime endeavor. Yes. Because $1 trillion is still a lot of money to anybody.
Well, and we live in a society here in the United States where, these are private, publicly held companies, and they have a vested interest to see to it that every molecule of gas is traveling through that pipe safely. They don't want to lose it. They're incented to keep it in there, right? And so I think we've both been in other parts of the world where there is no incentive, and that's a dangerous place to be, right?
Yeah. Yeah.
There's a lot of implications when you don't have those measures in place, when you go from privately owned to state owned, and so a lot of loss of those suppliers, those vendors, those LDAR people, those technologies that are in place, methods and procedures to just for safety purposes, but prevention. I think very passionately we still do it the best in this country.
There's no question.
Yeah. As far as how this product is doing, let me just comment on that. So we have been delivering to market since last year reliably. We've had great delivery. Production, we build them in batches of about 20, maybe 25 at a time. And so when customers order this product, they're going to get it from Florida. It's 100% assembled in Florida. And sometimes people want to know, okay, well, where are these things coming from? And so they're going to be shipped from Florida. We get parts made in Latvia. It's a very strong ally, NATO ally country of the U.S. And so we have other parts made in Europe. And you can't avoid having certain parts come from China. All manufacturers in this type of technology, little tiny components, chips. But we've had strong delivery, and we will continue to going forward. And the other side of it, the testing certification. So we're on top of the certification with the Underwriters Laboratory. That's a very important feature that people are anticipating, and that is supposed to get wrapped up this month. Could flow into the first 2 weeks of August, but the Underwriters Laboratory has issued us a letter to say that they're going to complete their testing in July. And so if it happens to be the first 2 weeks of August, I wouldn't be surprised, but that's a very good thing. So operators can use this technology and have the assurance that it is intrinsically safe for use at their facilities.
So Underwriters Lab gives you a Class 1 Div 1 or Class 1 Div 2 certification?
So we're shooting for Class 1 Div 2 right now, and that is pretty much the standard across the industry here. And you look at OGI cameras, what's the best that they get? Class 1 Div 2. And so as long as you have that Class 1 Div 2 certification, it means you don't need a hot work permit taking that piece of equipment inside the compressor station or well pad, whatever it may be. It's very useful in demonstrating that this device is not going to be the cause of any problems or explosions in a gaseous environment. So that's the minimum standard that they require typically in the natural gas industry. So we expect to meet that standard and have the equivalency for these other global standards. There are other global standards out there outside of UL. We're talking US.
What's the European standard, and do you have an
ATEX.
intention of getting a European approval?
So we'll revisit that after we get the final result from the Underwriters Laboratory. The expectation is that they're going to write a letter to say this is equivalent to these European standards or these Australian standards or this global standard, and that it will be accepted. And we'll see how it goes. We got to start somewhere, right?
So if you start with UL and Class 1 Div 2, it's much easier for the Europeans or the Australians and the others to approve it. But if you start with ATEX or one of the others, you may or may not be able to get the Underwriters Lab Class 1 Div 2 so easily.
Yes, and I'm finding out recently that Australia doesn't accept ATEX approval right out of the gate. So I think it comes back to equivalency. So each country to their own, but there is a global standard that we're aiming to comply with. So we have to pick somebody to do this testing.
Yes.
Because we're here in the U.S., that it's appropriate to do it. This is where our main market is. So Underwriters Laboratory is a long-time company that's been doing this probably before anybody else. So we expect that their testing, their rigorous testing and certification, we're going to meet this higher global standard that will be accepted and be equivalent where we need to get that product, including Europe and Australia.
Beautiful. Thank you very much for your time, Milton. It's been an honor and a pleasure.
Absolutely. Appreciate it. Good to be with you.